Today, we're going to continue calculating some line integrals. This was a combination of looking at vector fields, which is a new kind of function for us, and parameterized curves, which is technically not new, but we're looking at parameterized curves in more detail than we did way back in Calculus 1. So a line integral is a combination of a parameterized curve and a vector field. We're still just doing an integral, so we're still just evaluating a function at a bunch of points and then adding up the results. Calculating a function at a bunch of points, multiplying by a dx, and then adding up all the results. The integral part is telling us what points to plug into the function, and then we multiply and then add them up. So now our function is going to be a vector field. That's the thing that we have to evaluate at a collection of points. The collection of points is going to be an oriented curve. So remember, when we draw a curve in a parameterized curve in R2 or R3, it has an orientation, there's a direction, there's a start and an end. Our strategy is the same strategy that we used way back with integrals. We consider the vector field to be we consider the vector field to be constant at a bunch of points, and we use that value of the vector field for some small changes in the input. So if the inputs don't change that much, then the value of the function won't change that much. So we can kind of assume them to be constants. And then if we want a better approximation of what's going on, then we just make the dx smaller. In a line integral, the other thing to remember about integration is that integration is just multiplication, but one of the factors is variable. The multiplication that we're using in a line integral is a dot product. So that's the cool thing that we've introduced. By upgrading our functions to vector functions, is that now we're going to look, our multiplication is going to be a product of vectors. And so we're going to calculate a dot product. That's our multiplication for this integration. So instead of just f of x times dx with regular old scalar multiplication, we have the vector field f dot dr. All right, so last week we did one whole problem of calculating a line integral. So let's do another whole problem. Actually, kind of a half problem because I'm using the same vector field and the vector field is constant. So, start small and then build up from there. So we have the vector field 1i plus 2j. So that's going to be this constant vector field. It also makes it easy to draw. And we've got C, the curve is going to be this line segment from 1,8 to 9,2. So we're starting off at the point 1,8 and we're going to the point 9,2. What we want to do is parameterize the curve C. So we want to parameterize the curve C. So we're going to start off at 1,8. Let's say this happens when t is equal to 0, and let's suppose that 9,2 happens when t is equal to 1. We can have our starting t and ending t be whatever we want. It might be that the particular situation that we're looking for, 1,8 happens at the start, but 9,2 doesn't happen until t is equal to 10. That's not going to make a difference. Going from 1,8 to 9,2 when t goes from 0 to 1 is it's just going faster. So the values of the parameter, those are easy to shift around. We can shift those to be convenient for us. So might as well start off at 0 and end at 1. So we need to parameterize this curve. And so I need a function x of t. So x of t is it's going to start off at 1. X of t starts off at 1. And it's going to increase by 8 as t increases by 1. So I'm going to say plus 8 times t. So this 8 is 9 minus 1 over 1 minus 0. This is delta x over delta t. We're writing x as a function of t, not a function of y. X goes from 1 to 9, so that's an increase of 8 as t goes from 0 to 1. It's really important to understand our rates of change when we're building a line. That slope is not just slope. Slope is delta x over delta t, because x is a function of t. So that when we go to write y as a function of t, we can say y of t starts at 8 and decreases by 6 to 2 as t increases by 1. So this negative 6 is delta y over delta t. So remember the function that we're dealing with. The input is going to be t and the output is x. When t is equal to 0, x is equal to 1. And when t is equal to 1, x was equal to 9. So the delta x is 8 over a delta t of 1. And then for y, when t is equal to 0, y is equal to 8. And when t is equal to 1, y is equal to 2. So the delta y is negative 6. So our curve C, if we parameterize it, so I'm going to have x of t times I, so 1 plus 8t, and y of t times j. And so this is going to be our curve, parameterized. And this is for t between 0 and 1. Now we just need to calculate our line integral. We have parameterized the curve C. So our integral over C of our vector field F dot, oh, I'm gonna have to write dr. Our integral over the curve, the way we're describing the set of points to plug into the function has now been parameterized with t. So this is going to be the integral from 0 to 1. So we're writing a dt integral. Our vector field F is still just 1i plus 2j. And we need a dot product, not with r of t, but with dr. So if r of t is 1 plus 8 t I plus 8 minus 6t times j. dr, well, we got to figure out what dr is going to be. Anyone want to take a wild guess at what we're going to do to find dr? So for dr, we'll just take a derivative. That's what dr represents. It's the derivative, and specifically with respect to t. So dr, the derivative of r with respect to t, is just going to be the derivative of the x and the derivative of x of t and the derivative of y of t. So it's going to be 8i minus 6j, or the part that we need for the integral is just the dr, and that's going to be 8i minus 6j times dt. If we remember what all the symbols represent and what integration is supposed to do, then vector calculus will hold no surprises for us. Now we just have to calculate this dot product, which happens to be a nice constant. So we'll get the dot product of 1i plus 2j times 8i minus 6j is going to be 1 times 8 plus 2 times negative 6. So it's going to be 8 minus 12. So our line integral goes all the way down to the integral from 0 to 1 of just -4 dt. So the integral of -4 with respect to t is -4t, evaluated from 0 to 1. So we get a value of -4. We should take a look at, I picked this one because we could draw it. We should take a look at the drawing to see if this makes sense. Does it make sense that we get a -4? Is the vector field pushing along the curve or against the curve? So the curve is traveling from left to right, and the vector field horizontally, the vector field is going from left to right. So horizontally, the vector field pushes along the curve. It's like pushing this along. But vertically, the vector field is pushing up while the curve is headed down. And if we look at the vector field, the slope of the vector field is 2. The change in y is 2. The change in x is 1. So it's got more up than it does right. And so it makes, so at least the answer passes the reality check. We had got something positive here, we might be suspicious, because there's a lot more up in this vector field than there is, there's a lot more pointing up than there is pointing right. And the slope of our curve is -6/8. So the slope of the curve is close to just -1 going down. It's fairly even going down. So it looks like there's some canceling happening with the horizontal push with, and the vertical push against. Also note that the calculus is pretty simple here because I set things up to be a simple calculus problem. But the most involved part of the problem was parameterizing the curve. All the work went into setting up the integral. Then the integral just turns into a single integral because we're doing line integrals. And so we just crank out a single integral. Any questions? Great. Let's take another example. So I need a vector field. And I need, let's see, and I need a curve. So we're going to use our other classic curve, oops, a piece of a circle. So the question I have in the chat, are there any techniques I found to help remember everything in perfect details? I'll let you know if I ever find one, because that would mean that I remember things in perfect detail, and I don't. So my technique is a bit of an illusion. I make it seem like I remember everything in perfect detail. And apply the Indiana Jones and Last Crusade technique. I wrote it down so I wouldn't have to remember. The other thing that helped me remember things I do remember things in great detail. The part of calculus that I remember in best detail is Calc 2. Second best detail, Calc 1. Third best detail, Calc 3. It's easy for me to put those in that order because I just have to count the number of semesters I've taught Calc 2, the number of semesters I've taught Calc 1, and the number of semesters I've taught Calc 3. And that's why I can remember all this stuff. It has nothing to do with my mind being a steel trap that remembers everything, because we know that that is flat out false. I will walk downstairs and forget what I went for. If my wife sends me to the store to get 3 things, I will come back with 2 of them and forget the third. If there were only 1 thing I had to pick up, and the second thing is communicated to me verbally as I'm walking out the door, pick one of those things, I'm not getting it. It could be I'll remember the one that was first and forget the one that I heard, or I'll remember the one that I heard and forget what I originally went there for. My favorite is when I'm going to go to the store to pick something up and someone says, hey, could you pick this up as well? I'm like, sure, I will just not pick the thing up that I went to the store for in the first place. So the reason that I remember so much from Calc 2 is that I've taught Calc 2 every semester for at least the last 15 years. And repetition is really where it comes from. That's why a lot of the times when I'm explaining something here in Calc 3, instead of saying vector field, I'll say function. Instead of saying dr, I'll say dx. Instead of saying dot product, I'll say just times. Because I've taught Calc 1 a lot, and I've taught Calc 2 a lot, and I'm always going after this integral, the way we think about integrals. So if you really want a technique to help remember everything, it's a product of repetition and time. If you can increase the number of reps in a short amount of time, or the same number of reps across however much time it takes. It's kind of like work. Work is equal to force times distance. Increase the force to do more work in a short distance, increase the distance to get more work out of less force. Let's probably go with power and time. Power and time is another way to calculate work, right? I don't know. Someone from physics will correct me in the chat. So we've changed up our curve. So now we're going to go with the semicircle from 1, 0 to 0, 1. So let's draw a picture of that. Don't need an extensive picture. So we'll start off at 1, 0. And we'll end up at 0, 1. I've been drawing the curves in red. 1, 0. Oh. Originally, I was going to give you a semicircle. But then I picked 0, 1, so we're doing a quarter circle. Our curves have to have an orientation, so we're going from 1, 0 to 0, 1. I just picked a piece of the unit circle because that's easy to parameterize. We remember how to parameterize the unit circle. X is cosine of t. And y is sine of t. The other part of the parameterization that we need are the values of t. And so if we parameterize, the usual parameterization of the unit circle starts off at 1, 0 when t is equal to 0. And we hit 0, 1 when t is equal to 90 degrees, or pi over 2 radians. So here's our parameterization for t from 0 to pi over 2. So our line integral is going to turn into a single integral from 0 to pi over 2 dt. We need to write down what our parameterization is as a vector, because we're going to drop part of it into its derivative into a dot product anyway. So our curve is going to be cosine of t times I plus sine of t times j. The thing that we need for our line integral is going to be the dr. So dr, the derivative of cosine is negative sine, and the derivative of sine is cosine. And all this gets multiplied by dt. I just went through, I took the derivative of r with respect to t. And then just like when we were doing substitution, I just pushed the dt over to the other side. I imagine the dr over dt as delta r over delta t, and just multiply both sides by delta t. So these are small little pieces of my curve. I'm just thinking of my curve as a bunch of line segments. Now we can set up our line integral. The integral along C of the vector field f dot dr is now the integral as t goes from 0 to pi over 2. My vector field f is yi plus xj. And my dr is minus sine of t I plus cosine of t j dt. And now at this point, we should look at the line integral that we're building and say, hang on a second. This is supposed to be an integral dt, but our vector field is still yi plus xj. So what gives, Professor? So we got to think about what we're going to do about this x and y. Remember that we only care about the values of this vector field along this curve. So for these values x and y, we're just going to grab the curve. So our integral is going to be the integral from 0 to pi over 2 of yi. So let's see, sine of t times I plus x, which is cosine of t times j dot dr. And now we have a scalar function of just t. So we're integrating from 0 to pi over 2. Sine of times sine is negative sine squared. Cosine times cosine is plus cosine squared t dt. Now we've got this integral of cosine squared t minus sine squared t. Some of you might remember that we integrated cosine squared t by parts, which was a very bad idea. I mean, it worked, but it's not how things work. So what we need to notice is that cosine squared minus sine squared is just cosine of 2t. Remember, you have to remember everything all the time in perfect detail. And this is handy because cosine of 2t is a super easy integral to integrate. Now that I've said that, watch me drop the sign. Like that. All that for a 0. I like to do this problem because sometimes even the instructor does all this work on a problem and they get 0 as well. Any questions? All right. So keep in mind, don't get lost in the details here. Notice that most of the work came from parameterizing the curve. Once we parameterize the curve, not only did I use the derivative, take the derivative to find the dr for the dr factor, that also, the dr factor also is where we carry our dt into the problem, so we can integrate a single integral, t integral. But because we're only, if any x's and y's that we have in the vector field, we just use the same parameterization that we used for the curve, because we only care about the values of the vector field along the curve C. So we don't have to worry about what's going on at the point 0, 0 at this vector field, because that's not on the curve C. The integral says evaluate this vector field at all the points along the curve C. And so here are the points along the curve C. That's all we have to care about. The part in blue, the dr, that is a bunch of line segments that's going to form our curve. But putting the sine and cosine in for x, for y and x in the vector field, that's us evaluating the vector field along the points on the curve, which is all we do in integration. We plug a bunch of values into the function, we multiply by the dx, and then we just add all that up. So I remember that we parameterize the curve as x is cosine and y is sine, because this is just a piece of the unit circle. And x is cosine, y is sine is our standard parameterization for a unit circle, starting at 1, 0 and going once around counterclockwise. I'm also cheating on remembering the parameterization of the unit circle without looking it up because I happen to be teaching a trigonometry class. So if you didn't remember that parameterization of the unit circle, it's mostly because you're not teaching a trigonometry class this semester. Any questions? Comments? Technically, it's the other way around. I've been teaching. I've only been doing trigonometry the last couple of semesters, and I've spent more time doing Calc 3. And so Calc 3 is where I reminded myself of the cosine sine parameterization of the unit circle. And so when I got to trig, I'm like, oh yeah, I remember that from Calc 3. And everybody's like, oh, dude, that's backward. Trigs Calc comes before Calc 3. And I was like, well, not for me. In my recent memory, it's the other way around. But like I said, all of it, all the time, in perfect detail. Any questions? Comments? That'd be really cool if there was like a really stylish way to draw a unit circle and just have one like inside your forearm. And it's like, oh, unit circle. If you tattoo the notes, like if a professor was like, oh, no notes during this test or final or quiz, and some student came in with that stuff tattooed on their arm, I'm like, oh, that's a lot of commitment. I'm gonna let you use that. I'll allow it. Because I mean, that's commitment right there. Then if I find out it's a temporary tattoo, negative points, not just a 0. Some teachers are like, oh, you're cheating on this test, you get a 0. I'm like, oh, forget that. If I catch you cheating on a test, I don't give you a 0. I give you negative the maximum score. So if it was a 100-point test, you get negative 100 points. If you're going to try to lie to me like that, I'm going to take one of your previous perfect tests and cancel it out. The rules say I can't flunk you in the entire class if I find you cheating on one paper or test or something like that. But it doesn't specify the method that I use to flunk you on that test. So instead of 0 out of 10, you get negative 10 out of 10. It just cancels out something. Any questions? Comments? Snide remarks? All right, that's gonna do it for today. Oh, important question. I did not dress up for Halloween this year. Although planning has already started for next year's costume, my wife and I are going to be Laszlo and Nadja from What We Do in the Shadows. All right, that's going to do it for today. I will see y'all on tomorrow for some more line integrals. Everybody have a good day, and thanks for playing.